An airplane traveling at a constant airspeed of 360 miles per hour climbs at an angle of 30 degrees to the horizontal. At one moment, the plane is 10,560 feet directly above an observer. How fast is the distance changing between the observer and the plane 3 minutes later? Well, looks to me like I'm trying to find DDT. So I'll probably want to say that I can build a relationship among these three sides of the triangle because I know something about them. Notice how this is a side length whose rate of change I'm trying to find. But notice how this 360 miles per hour, that's a rate of change. So technically speaking, is it not true that the picture is somewhat deceiving, albeit I'm the one who created it? If I refer to the length of the side as x, it certainly is the case that dx dt is 360 miles per hour. So I know something about x. Seems to me that if I build a relationship among these three sides, at least I know what dx dt is. Now, technically speaking, that's measured in miles per hour. So what I could do is convert this to feet. If I do, that's a really large number. I'm tired, I'm lazy, I don't want to do it. Besides, whoever made up this example made sure this number was extremely nice. Isn't that just simply 2 miles? Now, the relationship we have, or at least a relationship we have among these three sides, is the law of cosines. And the law of cosine says the following. That d squared is indeed equal to this plus this minus twice the product of those two times the cosine of the angle in between. But wouldn't that give us this? Shoot, sorry. Now, that being the case, if I treat x and d as functions of time t, because when you look at my picture, they are changing as time goes by, I will differentiate implicitly with respect to time t. Now, in differentiating implicitly, I think it's going to give me this. And let's see if you and I can just take a quick break and see if we have all the information given. Well, I don't have this, but that's okay. That's what I'm trying to find. I do have this. It's right there. I don't think I have x, but I think we can get it very quickly. After all, pulling out a nifty piece of scratch paper. I know that something happens after I don't know how long. 3 minutes. So I'm trying to find BDDT 3 minutes later after the plane passes over this observer. And so let's see what x is after 3 minutes. I think what x is going to be, that distance, is rate times time. Well, the rate is 260 miles per hour. And the time is 3 minutes. Shoot, I'm running out of room. I don't know, everybody. I really want to show you this. I'm not changing anything. I'm just moving to the left a little bit more. So the distance is rate times time. The rate is 360 miles per hour. The time is, I've lost it, 3 minutes. But now to get rid of the minutes, can't I just put minutes downstairs so I cancel the units? Hours upstairs, cancel the units. But 1 hour is equal to 60 minutes. I'm just doing simple what do you call it, unit analysis like you would do in a traditional chemistry course. And that being the case, I think I'm left with, let's see, is that going to be a 6 times 3 is 18 miles? So I do think at this one point in time, I know x is 18 miles. At this one point in time, the D value is, well, I guess I'm kind of stuck. I don't know what it is. So I guess I have to pull out a second piece of scratch paper. Now, at this one point in time, those are the coordinates I have. And so yet again, by the law of cosines, doesn't that apply this? Uh-oh, is that number right? 160. That should be 120, shouldn't it? My goodness. I guess in my head I knew that it was. Oh, am I going to have to do some arithmetic? I can't break it down any further. So I do have a D value 2 root 91. And I think I'm in business. I guess in the end that means d dt is equal to this. Now, if you guys don't mind, can I just very briefly get an approximation of that? Oh no, I can't read it. Sorry. I don't know, just using our number sense, does that number seem reasonable? See, I think it does. I think that d dt should be very close to dx dt for this simple reason. My picture's way deceiving. At this one point in time, x is 18. But this leg over here, not leg, but this side length here is only 2. And so I think this is a very elongated triangle. And with such an elongated triangle, I do think the rate at which this change and the rate at which this change are pretty close to each other. And it certainly turned out to be the case. A very test-worthy question. I like it. I hope you like it. I'll leave the rest of the examples in the sheet for you.